to stay on? Because there's,
yeah.
you know what?
Okay.
I think so.
Because for filming it, I think they need.
Oh, that's right. Okay. Well, we'll see how it goes. There's just some contrast issues, but we'll see how. You know.
I know.
Okay.
Let us know.
All right.
Okay. Welcome. How many have been here before? Oh, welcome, all the newcomers. Right. Great news. The moon is rising. Jupiter's up there. Kind of washes the moon. The moon is going to wash out deep sky objects, but Jupiter is up there, and it's going to be up all night. So you can make yourself comfortable with our speaker, and then find your way outside and upstairs to the 26-inch scope. Take a peek at what we have. By the way, we're an all-volunteer organization, and we get our financing through donations and through membership. So if you like what we offer tonight, a donation would be appreciated. I mean, what are we going to offer? We're going to offer you friendship. We're going to offer you the moon. We're going to offer you Jupiter, the stars. Small stuff. You get that all the time with other charities, right? Stars. So, just think about that. Anyway, did you ever get, sometime at night, when I'm out under the stars, I feel like I'm being watched. You kind of stay there, look over your shoulders, and you wonder. And after a while, I realize that it's not from around me, but it's from up there. And I'm sure that there's a watcher. I'm sure that there are people or things or something up there looking back at our little normal star, wondering if there's intelligent life on any of the planets. So far, I don't know if there's life on Earth, but wondering. Well, tonight's speaker is a watcher. Somewhere out there, there's this probably green creature with dreadlocks and long fingernails, and is standing there going, I feel like he's being watched because someone is watching. Tonight's speaker is searching. Dr. Joshua Pepper from Lehigh University, an astronomer and an exoplanet watcher, searcher. So please give a hand to Joshua.
All right. Thank you. Can people in the back hear me? Is this working okay? The lavalier? All right, great. So, what's that? The green light on? The green light is on. All right, so if you can't hear me, just wave and give me a signal. So thanks for having me. I'm a professor at Lehigh University. I'm an astronomer working in the field of exoplanets. This is something that I've been involved in for the past 10 years. But when I started off in college, when I was thinking about whether I wanted to be an astronomer, this field basically didn't even exist. So this is a very new field. There's been a lot of changes recently, and it's really become the forefront of modern astronomy. And so what I want to do tonight is tell you about the kind of research that I'm doing in this field, about what we now understand about the population of exoplanets that are out there, which is changing very rapidly, because you can see news articles every once in a while about, oh, there's this new planet that was the biggest or the smallest or the faintest or the most Earth-like, and it can be hard to kind of get an overall sense of what do we know about these exoplanets that are out there. So what I want to tell you tonight about how we find exoplanets, what we know about them, and the kind of work that I do to discover a certain special type of exoplanet. So to lay the groundwork for those of you who might be as old as myself or older, you might remember back in the old days before 1989 when all the planets in the universe that we knew about were these. It was only the planets in our solar system. The inner planets, Mercury, Venus, Mars, Jupiter, and Saturn, those are the planets that have been known since ancient times, because you can see those with the naked eye. If you have a star atlas or or you know where to look, you can see any of those planets with your naked eye without a telescope. Then, after the development of the telescope in the 16th and 17th centuries, people were able to see fainter and fainter things, and so they discovered Uranus and then Neptune and then eventually Pluto, although now that we learned more about the outer parts of our own solar system, we arguably don't no longer think that Pluto's a planet. Stay here. Okay. But if you think that Pluto, if you have any questions about that, you can ask them later on about this whole debate about whether it makes sense to call Pluto a planet. So how did this happen? Well, over the if you sort of plot the total number of planets known over the past few years or past few centuries, you'll see a shape like this. And obviously, there's been a huge explosion in the discovery of exoplanets just within the past 10, 15 years. So that's what I want to tell you about. How did we start discovering all of these planets, and why did it just happen within the past few years? Well, it turns out there's a lot of different ways you can find planets. There's actually arguably 15 or 20 different separate methods that can be used for planet discovery. But the most productive ones are a few, and I'll tell you about those. So these methods have been very successful. We now know of over 15 or 1,600 planets outside of our own solar system orbiting other stars, most of them in our little part of the galaxy, the Milky Way galaxy. This number is actually kind of, it's arguable what that number is, because it can range from about 1,600 up to 3,000 or 4,000, depending on what you count as a confirmed or discovered planet versus a very likely planet. So there's several different ways of finding planets. The most obvious one that people might think about is just go look for them. You just go look at a bunch of stars, and you look next to the stars, and maybe you'll see a planet orbiting the star. Well, that would be an awesome idea, except for the fact that stars are very, very bright, much brighter than their planets, and the planets are very close to them. So the comparison of looking for a planet orbiting a star that a lot of people like to use is, imagine you're standing about 10 miles away from a hill at night, and on that hill is a huge 6-foot wide searchlight that's pointed directly at you, and in order to find a planet, what you're trying to do is see the patterns on the wings of a firefly crawling along the edge of that searchlight. It's obviously very hard because it's so faint and close. The state of the art where we're at right now, and I apologize for if the contrast makes it hard to see, this is the state of the art. What you're seeing here in this little blob over on the right is the residuals of what's left over after scientists have observed a very, very bright star that's sitting right here in the middle of this blur, and this blur is the residuals. It is what is left over after 99.9999% of the light of the star has been blocked, and that's still that 1/1,000,000th of the light that's been blocked that's left over is still way brighter than a few of these dots over here. You can see these dots labeled D, C, and B. Those dots are planets orbiting that star. Each of those dots is a big gas giant planet, kind of like Jupiter or Saturn. And the reason they look like this dull red is because those planets are still very hot. This is a young system. It's compared to our solar system, which is 4.5 billion years old, this system is only about 10 to 15 million years old. And these planets have just recently formed, so they've still just come together, so they're still glowing pretty hot. They're gas giant planets, and this little bar down here, it says 20 AU. That's 20 astronomical units, or 20 times the distance from the Earth to the Sun. So the closest of these three planets, planet D over here, is about 30 AUs away from the star, which is in the middle over here. That's about the distance of Pluto from our sun. So the best that we can do right now for directly seeing planets near stars is to be looking for cases where you've got a big, hot, distant planet from the star. If you wanted to see the Earth orbiting the sun, you'd be looking for a dot that was maybe 100 or 1,000 times fainter than this little red dot here, and was located right down here in the middle of all this mess that's been left over. So that's why direct imaging is very, very hard. In these cases, these planets are about between 1 million and 10 million times fainter than the star itself. The Earth is about 10 billion times fainter than our sun. So that's the reason it's very difficult. You're talking about a huge contrast in brightness, and these things are very, very close on the sky. So that's why direct imaging is very hard. Then there's other ways of finding planets that are called the indirect methods. These are cases where you can find a planet, but you're not actually seeing the planet itself, you're seeing the effect of the planet on the star. So when you have a planet orbiting a star, then you might normally think of it as a planet goes around and the star is stationary, but really what's going on is that the planet and the star are both orbiting their combined center of mass. So as the planet goes around a star in a really big circle, the star is wobbling back and forth in a little circle due to the gravitational influence of the planet. this is analogous to the situation where, oh, and so when this is happening, you're not actually seeing the planet itself, you're only seeing the star. And then you're inferring the existence and mass of the planet from the movement of the star and how much the star is moving. So this dance of gravity, where the planet makes a really big circle around the star and the star makes this little wobble back and forth, is similar to, is due to conservation of angular momentum. This is the situation where if you've got two figure skaters spinning around each other, then the larger figure skater will be making a small circle and the smaller, less massive figure skater will be making a bigger one. It's a very similar analogy. Of course, since planets are way less massive than their stars, then the analogy we'd want is not, a slightly larger figure skater spinning around a smaller figure skater, but something like, an enormous person, throwing around a little boy. And so through the magic of Google, we can see what that looks like. So as the sumo wrestler is making a very tiny circle over here, the boy is making a really, really big circle like that. So the motion of the star that we're seeing is analogous to the tiny little circle that the sumo wrestler makes as he spins around. So when that happens, what we can do is we can measure the light from the star. We don't see the planet, but we see the star. And as the star moves back and forth along our line of sight due to the gravitational influence of the planet, then the light from the star is going to be Doppler shifted. This is the same effect that it causes a siren to sound high-pitched when it's moving towards you and low-pitched when it's moving away. So in that same sense, the light from the star is going to be shifted a little bit to the red and a little bit to the blue as it moves towards us and away from us. And if we make that measurement, which is a very, very tiny shift in the light, this is obviously very exaggerated here, then you plot it out, and this plot of how fast the star is moving towards or away from you, if there's a planet orbiting that star, it'll make this nice sinusoid-looking pattern that will be evidence for the planet, and the size of that wobble or of that shift back and forth is related to the mass of the planet. So this is also, so this is a fantastic way of discovering planets. The difficulty, of course, is that just like with direct imaging, the effect is small. The shift caused to a star's velocity due to the gravitational influence of a planet is typically something like several hundred miles an hour, which sounds, might sound like a lot, but that's actually a very small change in velocity to measure over the course of light years. And if you're looking for a small planet like the Earth, then the amount of movement is just 0.22 miles per hour. That's slower than a person walks. So if you want to discover an Earth-sized planet orbiting a star using this wobble method, then you have to be measuring the speed of the star towards or away from us at a speed that's slower than that of a person. So that's a very difficult thing to do. Now, my favorite method for discovering planets is the so-called transit method. In this case, you've got a planet that's orbiting a star, and in assuming that the orbits of planets around stars are randomly oriented, then in very few special cases we'll have the planet orbiting the star along our line of sight such that it crosses in front of the star from our perspective, and it blocks the light of the star. When that happens, it causes the star, from our perspective, to dim a little bit. We don't actually see this happening in real, we don't actually resolve this. What we see is that the star has a certain amount of brightness for a certain amount of time, and then it dims a little bit. And then it goes back to its normal brightness. The power of this method, which makes up for the fact that you can only discover a very small fraction of planets this way, because you can only discover those planets that happen to be oriented just right. The power of this method is that the amount of time that it takes for the star to go from fully bright to dimmed, and then to go from dimmed to back up again, is directly related to the radius of the planet. So while the wobble method tells you what the mass of the planet is, this method tells you what the size of the planet is. And if you've got mass by going back to this star and looking for the wobble, and then also getting radius by measuring this transit here, then mass and radius, you combine that and you get density. And if you know the density of the planet, then you can say something about what it's made out of, because gas has a different density than water, than ice, than rock, or metal. And so you can tell if you've got a rocky planet, or a gas giant planet, or a water world, or something like that. Now, again, just like every other method, these kinds of measurements are very difficult to do. In a best case scenario, where the size of this effect is the largest it can possibly be, then the size of this dip is about 1%. That is, the planet is a big gas giant planet orbiting a star that's a medium-sized star like our sun, and when it crosses in front of the star, it dims the light by 1%. So to think about the size of that dimming, to think about how much that star is dimming from its normal brightness, imagine you're sitting and looking at a skyscraper at night. Looking at a building at night, and as the building is 10 stories tall and it's got 10 windows across. So you see 100 windows. And imagine you're staring at it with glasses that have some Vaseline or something spread across them, so you're seeing a big blur. So to see a 1% dimming of the light means that someone in one of those 100 windows turns off the light in that room for a few hours and then turns it back on. And you're just trying to see the total effect of one of those 100 windows being dimmed through your sort of blurry vision there. Now that's the best case scenario. If you wanted to see a planet, not a gas giant planet like Jupiter, but say an Earth-sized planet causing a transit like this, then in that case, instead of seeing a building that's 10 stories tall, imagine a building 100 stories tall and 10 windows wide, and you're still looking at it through your blurred out Vaseline-covered glasses for some reason. And you're trying to see the effect of the dimming that will be caused by someone in one of those rooms that you're seeing lit up pull the window shade down by 3 inches and then letting it back up a few hours later. That's why this is very difficult. And so the reason why it took many, many years for us to start discovering planets using any of these methods is because we had to wait till our technology had improved enough. And the improvement of the technology in practice was really, really hard. You might think it was really about telescopes. What it really was about this. The chips in our cell phones, the kinds of cameras that we use, are called charge-coupled devices, or CCDs. And it required us to build CCDs, these cameras, that were sensitive enough to detect tiny little changes in brightness at a very reliable level in order to detect these kinds of effects. But that basically came about in the mid-1990s, and that's when these planets started to be discovered. And to get an idea for what an actual transit looks like, a real transit, then this is a picture of one. Now this is not an exoplanet. This is a picture of the planet Venus transiting in front of our sun a few years ago. This happens twice every 112 years at sort of like 7-year separations. It just has to do with the relative inclinations of the orbit of Venus and the orbit of the Earth. So imagine trying to see this effect, but when this happens with an exoplanet and another star, you don't actually see this nice resolved image. You just see a single point of light, and the dimming is being caused by that little black dot there. So that's why this is so difficult. So some of you might have heard about the Kepler mission. This is a fantastic project that was rejected many, many times by NASA because no one believed it could be successful. And in the end, it was successful. It was a satellite that was launched back in 2009, and it's still operating today, although in a different configuration. And the idea behind Kepler was to measure the frequency of planets by using the transit method. It stared at a single place in the sky, in the constellations Lyris and Cygna, in a patch of the sky that's about the size of your hand, held at an outstretched distance. And it looked at that area in the sky, and it monitored the brightness of about 160,000 stars in that patch of sky continuously for 4 years straight without blinking to catch all the transits that happened among those stars. And it had a very specific mission. It wasn't just to find any planets. The idea was to determine this weird number here. It's a Greek letter called eta sub Earth. And eta sub Earth is described as the frequency of Earth-like planets in the habitable zones of sun-like stars. Now, if you've ever heard of the Drake equation, the eta sub Earth is a factor in the Drake equation. The Drake equation is supposedly a way of putting together a whole number of factors: the number of stars in the galaxy, the lifetime of a star, the frequency of planets around stars, the fraction of planets that are Earth-sized, and so on and so forth, to try to figure out what's the likelihood of there being an alien civilization in our galaxy. How likely is there to be an alien? Are there to be aliens? Well, it's been 50 years since that equation was proposed. It's got about 9 or 10 different factors all sort of smushed together in that equation. Eta sub Earth is one of them. This is really only the second of the factors, of those 9 or 10 factors, that we actually now have a handle on. All the other numbers are still are completely unknown. We have no idea what the how likely it is for there to be life on a planet, or how likely there is for that life to evolve intelligence and so forth. But this is the starting point. This is what we're trying to figure out. Now, so eta sub Earth is just basically how likely are Earth-like planets? How common are they? There's about 200 billion stars in our galaxy. So if that frequency is 1%, then there's going to be 2 billion Earths in our galaxy, roughly. Now, one of the problems about the Kepler mission is that it was so successful, it broke this. It broke this sentence because it turns out that all of these quantities in here, the frequency of planets, what we mean by Earth-like, what do we mean by the habitable zone, all of those concepts, turned out we didn't really understand them. And we didn't understand them because there's a lot of complications in the universe that, that Kepler revealed to us by finally actually observing these stars precisely enough to truly understand what their properties were. And I'll tell you about what some of those changes are in our understanding. But the short description of the mission is that Kepler discovered thousands of planets. Kepler is by far the most productive planet discovery mission ever undertaken. These planets range in their properties. Some of them are gas giants. Some of them are rocky worlds. Some of them appear to be ice worlds. Some of them are in crazy elongated orbits. Some of them are in other kinds of orbits. So we now have a much clearer sense for the variety and sheer diversity of planets and planetary environments out there. So that's what I want to tell you about. I want to tell you about what are the discovery highlights. What do we now know about exoplanets that we didn't know 3 or 5 or 10 years ago? Well, the first of these discoveries was something that happened at the very beginning of the planet discovery. This happened back in the early 1990s when the very first exoplanets were found. And before we started actually finding planets, a lot of people speculated that other planetary systems, other solar systems, should look somewhat like ours. Our solar system has a structure. All the planets are orbiting in roughly the same plane around our sun. In the inner part of the solar system, you have small rocky planets. And these are rocky planets. You know, Mercury, Venus, Earth, and Mars are basically just big balls of rock around a core of metal, mostly iron and nickel. We might happen to have a little bit of air and water on top, but that's a very, very thin layer. Most of the terrestrial type planets, Mercury, Venus, Earth, and Mars, are just big balls of rock. Then you've got the gas giants. You've got Jupiter and Saturn, which are big balls of hydrogen and helium gas. And then you have the so-called ice giants, Uranus and Neptune, which are further out, and they're mostly made out of things we call ices. These are things like water ice, ammonia, carbon dioxide, methane, things like that. When we first started discovering planets, though, we found kinds of planets that will have no analog in our own solar system. If this is the inner part of our solar system lined up like this, and you zoom in past Jupiter, Mars, Earth, Venus, and then Mercury, then the first planets that were found, or some of the first planets, turned out to be super close to their stars. Mercury takes about 80 or so days to orbit our sun. It's the closest of the planets to our sun, and it's got the fastest orbit. Some of the first planets found were orbiting their stars every 3 days, or 4 days, or 5 days. They were incredibly close. They were really close, and they were not small rocky planets like we have in the inner part of our solar system. They were big gas giants like Jupiter and Saturn. They were orbiting so close that their surface temperatures were well over 2,000 or 3,000 degrees. So one of the big questions we had is, how do those planets get there? It turns out you cannot form a gas giant planet that close to a star. It's too hot. Once you started to try to gravitationally bring together a whole bunch of gas, that gas would get so hot that the molecules would be moving so fast, they'd be actually moving faster than the escape velocity of a small planet. There's no way they could stay bound together. You first have to bring all those gas molecules together and then build up the planet so that it's dense enough, it has a high enough surface gravity, and then you move it in close to the star in order to do that. But the question of how these planets formed farther away and then moved in close to their stars is a really big mystery. But these so-called hot Jupiters were some of the first planets that were discovered. We now know actually why it is. It turns out hot Jupiters are not all that common, but there's what we call an observational bias. These are really easy for us to discover. They're big planets and they're orbiting really close to their stars. And those two factors make it a lot easier to find them. So we've started finding these hot Jupiters. We also found a few cases of rocky planets that were that close, but some of them are really bizarre. This is my favorite one. This is Kepler-78b. Kepler-78b is a planet discovered by the Kepler spacecraft, hence its name. It is a planet that is just a little bit larger than the Earth and is about 80% more massive than the Earth. And since we know, because it both transits the star, tells us its size, and because we can actually measure the wobble of the star due to the planet that tells us its mass, we know the density of this planet. And this planet has a density very similar to that of the Earth. It's basically made out of rock and metal, just like us. But this planet is different because it is orbiting so close to its star, it orbits every 8 hours. Once every 8 hours. It is so close to its star that the surface temperature is going to be about between 3,000 and 5,000 degrees Celsius. When a planet's that close, the rock that it's made out of on the surface is all going to be molten. This is higher than the melting point of rock. So the surface of this planet is basically a lava world. But it gets crazier than that. And that's because we generally know what rocks are made out of. We measure the rocks on the Earth. We can tell through remote like telescopes and rovers and everything what the rocks are made out of on Mars and Venus and some of the outer bodies and asteroids and outer bodies in the solar system. We know what rocks are. They're made out of these certain kind of minerals, pyrovskites, olivines, feldspars, things like that. They're made out of these same kind of molecules. And so we know roughly what the rocks on this planet are overall made out of, not precisely, but overall. And we know that there's some materials in there called silicates. Silicates are certain kinds of rocks that are made mostly, as the name implies, out of silicon. Silicates have lower melting temperatures and also lower vaporization temperatures. And this planet is so hot, Kepler-78b is orbiting so close to its star that not only are most of the rocks molten, the silicates, it's so hot, the silicates are vaporized. So the silicate rocks have evaporated into a little atmosphere of vaporized rock on the near side of the planet, the side of the planet that faces the star. But because it's so close to the star, one side of the planet is always fixed facing that star. It's tidally locked, just like our moon is tidally locked to the Earth. And so those vaporized silicates will create huge winds that will blow them from the near side of the planet to the back side of the planet. So you're going to have a constant wind of vaporized rock swirling around to the backside, and the backside of this planet, we think, is cool enough that it'll actually be cool enough for those silicate materials to condense back out. So you're going to have a permanent rain of rock on the backside of this planet that lasts for billions of years. It's actually not really rock because it's silicates. It's basically glass. It's a rain of glass on this planet that's constantly happening. And then as it rains back down on the backside, then it becomes molten again and it flows to the near side and vaporizes again. In the same kind of weather, climate, thermal cycle, only here on Earth it's made out of water, and on there it's made out of glass. There's another big mystery. As we noted in our solar system, we've got these small rocky planets close to the sun, and then we've got these big gas giant planets further out. But we don't really have anything in between. If these circles represent, if the orange one represents Jupiter, then the blue one there represents Neptune, one of our ice giants, and the lower one with the sort of dark one with the blue annulus around it, that's the Earth. That green one, though, is the size of a planet that we don't have in our own solar system. We have planets that are the size of Earth and Venus and smaller, and we have the planets the size of Neptune and Uranus and bigger, but we don't have anything in between. These are the so-called super-Earths. And it turns out they seem to be super common in the universe. The more we look, these are by far the most common kinds of planets that we're able to find. We know that they're way more common, for instance, than gas giant planets or ice giants. We're not sure yet if they're more common than Earth-like planets because it's really hard to find Earth-like planets still. But what's kind of a mystery about them is we know what a gas giant planet's made out of. Based on the kind of material that's in their galaxy and in the interstellar medium and that comes together to form stars and planets, we know those things are made almost entirely out of hydrogen and helium gas. We know what these, what the Neptune-sized planets are, the so-called ice giants, we know roughly what they're made out of. And the small planets like ours, we know what they're made out of too. They're made out of rock and metal. You can't have a planet this big made out of rock. And you can't have a planet this big made out of just gas. The super-Earths, though, sit in this weird intermediate regime where they can be made up of almost anything. They could be mini versions of a gas giant planet. They could be small versions of like a water world. If you took Uranus and Neptune and moved them further in to be closer to the sun, you'd actually have a layer of liquid in there. You'd actually have some liquid water at some point. But you could have some of these are water worlds, and some of them might even be really large versions of terrestrial rocky planets. And this is a big mystery. We don't know why we don't have them in our own solar system. We don't know if that's just chance, or if maybe there's a reason why super-Earths didn't form in a solar system like ours. We're really curious about that. So if we start thinking about all the different planet types, we realize some odd things. Here, we're plotting the mass of the planet on this axis, and the radius, the size of the planet, on the horizontal axis. So let's see what kind of planets we have. Well, if you're looking down here, things that are the mass of, say, Mars, the mass of roughly Earth or Mars, but really small, then you're going to have what we call the iron spheres. That's basically what the planet Mercury is. It's a really big core of iron, nickel, metal surrounded by a thin layer of a mantle of rock. Those are the iron spheres. Then, things that are that mass, but a little bit larger, those are the terrestrial planets, like the Earth. Earth, Venus, Mars. Then, things that are that size, but lower mass, those are the water worlds. We're starting to find these planets that are roughly the size of the Earth, but significantly less dense. And the only way you can have that is if a lot more of the bulk of the planet is made out of things less dense than rock. And the most abundant of those things are the so-called ices: water, carbon dioxide, ammonia, methane, and things like that. Then you have the super Earths up there that are the size of those planets, but a lot more massive. Then you've got the water and ice giants, things like the size of Uranus and Neptune. You've then got the Jovian gas giants, the big gas giants like Jupiter and Saturn. And then you've got this other type of planet, the inflated gas giants. These are planets that are the mass of Jupiter or Saturn, but a lot larger, so that their overall density is extremely low. Some of these things are so underdense, they're less dense than styrofoam. So if we then only look at the kinds of planets that are in our solar system, we find that 3 of these types of planets do not occur in our solar system. So this is an ongoing question. Is our solar system unique? Is it unique, or is it just that we haven't found the kinds of systems out there like ours? Does that have anything to do with the fact that life evolved in our solar system? Does maybe the presence of these other kinds of planets somehow inhibit life? Or does the kinds of planets that we do have in our solar system promote it? These are the questions that we're trying to slowly address. Also, there's not just the planets themselves, there's the stars that they orbit. When you look out into the sky at night and you see all these beautiful stars, about half of those points of light that you see are not stars. They are binary stars. Most stars are in double or triple or high order multiple systems. Stars like to have high multiplicity. A lot of these are stars orbiting other stars. And they orbit each other in different configurations. Some of them are orbiting very wide. So the 2 stars are maybe hundreds or thousands of astronomical units apart. So it takes maybe tens or hundreds of thousands of years for them to orbit each other. So in that case, you could have a planet that's orbiting one of those 2 stars, and then another companion star is orbiting really, really far away. So we've already found several dozen of these binary planet systems, where you've got a planet orbiting a star and then additional stars in that system that are a lot further away. We also have the opposite case. Rather than the stars being really far apart, the stars are orbiting really, really close together. So close that the stars are orbiting each other once every 7 or 10 or 20 days. And you could have planets that are orbiting the combined center of mass of those 2 stars. So those are the so-called binary planets or circumbinary planets. These are cases where a planet has 2 stars in its sky. If you were sitting on that planet, you would see 2 stars constantly moving back and forth, coming around your horizon all the time. These are the circumbinary planets. There was really no way of getting around it. The inevitable name for them were the Tatooines. They seem to be, they're there. We've found about a dozen of them so far. We think there's a lot more. It just turns out to be a lot harder to find planets in this really much more complicated configuration. But we know that they're not that rare. At least 1% of all type binary stars have a circumbinary planet. So we know there's got to be at least hundreds of millions of them in our galaxy. One of the cool things about these is that I'll talk later on about the habitable zone. I mentioned it earlier. That's the distance from a star that a planet can orbit where the planet is, the temperature of the planet will allow liquid water to exist. So that is a concept that's really well understood for a single planet orbiting a single star. But how do you define a habitable zone for a planet orbiting a binary star? You could have a planet that's actually going in and out of the habitable zone several times a year as the 2 stars get further or closer to the planet. So that's a really cool question to think about. All right, so what has Kepler found? I've told you some of the highlights. Here's here's sort of the meat of it. Here's what the clear conclusions that we have from all this. Planets are common. We now know that planets are not rare. They're not unusual. We're certainly not unique in having planets in our own solar system. 70% of regular stars have planets, and that's just a lower limit. The number could easily be 80 or 90%. In fact, if you added all of the numbers up in the end, you could very easily have numbers higher than 100%. That is, you'll have so many multiple planet systems, you have way more planets in the galaxy than stars. So planets are common, planets are the rule, not the exception. Most of them are small. Gas giants do not seem to be the most common types of planets. There's a lot of them where a lot of the first planets found were the gas giants because they're easier for us to find, but most of them are the Neptunes or super Earths or terrestrial planets. Super Earths right now seem to be the most common type of planet out there. Planets come in packs. If you see one planet, there's probably a lot more there. So solar systems, systems of planets orbiting the same star, are very common. This is interesting. It turns out that the cool red dwarf stars, stars that are cooler and redder and smaller than our sun, seem to be way more likely to have planets. Almost none of them have gas giant planets, none of them have Jupiters, but a lot of them seem to have small super Earths and Earth-sized planets. So if we start thinking about the next 10, 20 years and start thinking about the first Earth-like planets in the habitable zone of a star that we discover that's absolutely clear discovery, it's probably going to be around a red dwarf star. So we better start thinking about how do we consider the possibility of habitability or life to exist on a planet orbiting in a 20-day orbit around a really small, cool red star. And in fact, the numbers are really high. At least 50% of red dwarfs seem likely to have a Earth-sized planet in their habitable zone. This number is still kind of hazy, but the number is large. So that's going to be very interesting. All right, so now what? So I've told you about thousands of planets being discovered, but there's actually tons of work being done still to discover more and more planets. So you can naturally ask the question, well, what's the point of discovering more? If you already have thousands, what is one or two or three more going to tell us? Well, there's really two directions for future discovery. One of them is to look for the rare or extreme or valuable planets. Planets of a type that haven't been found before, or planets of a type that would allow us to understand way more about planets than the ones that have been discovered so far. Another is demographics. If you've got 1,000 planets, but you've got, say, 15 different properties between the mass of the planet, the size of the planet, the orbit of the planet, the eccentricity of its orbit, the size of the star, all of those different properties, if you want to do good statistics, you want to have thousands or tens of thousands or hundreds of thousands of planets so you can actually trace patterns and correlations between all those different quantities. Like we talked about, where small stars seem to be much more likely to have planets. So for that, you want thousands or millions of planets, and so people are working on that too. But I work on the first of these. I work on a project called KELT. And KELT is a project that is looking for some of the most valuable planets that have yet to be discovered, because these will tell us a lot about the properties of planets. This is KELT. KELT is the kilodegree extremely little telescope. Astronomers love naming their telescopes after how big or large or gargantuan they are, and ours is a very small guy. You'll see here, it's actually, some people would not even consider this a telescope because it's not a reflector, it's a refractor. It's a regular telephoto lens attached to a scientific grade camera. So in this blue box over here is basically a souped up version of the CCD chip in our cell phone cameras, but one that's just very, very precise. It's a robotic telescope. There's actually two telescopes. They're both robotic. And the idea behind these telescopes is that they operate on their own, and every night they wake up, they open the roof, they start observing the sky, and they measure the brightness of thousands and millions of stars constantly over the course of the night. And they observe that part of the sky, and then that part of the sky, and then that one. And then they do it again and again. And they do that night after night, week after week, year after year. And what they're doing is building up a record of the brightness of millions of stars so that we can go in and search all of those brightness measurements of stars to see if any of them seem to have a telltale, regular dimming of the star that will be the signature of a transiting planet. This is a time-lapse video of what one of our telescopes looks like over the course of one night, over several hours. So this is the telescope that is pointing there, and then there, and then there, and then back again, over and over again. repeatedly, and this is not Ohio. That's right. That's the center of the Milky Way galaxy, which you can only see from the southern hemisphere. So we have, let me see here. Okay. So there's two telescopes, one in South Africa, which is the one you just saw, and then one in Arizona. So they're located in those places so that we can cover almost the entire sky. Now, one of the cool features of these is that there's a really small telescope. So why do we have a small telescope while everyone else is really excited about really big telescopes? Well, the difference is we're looking at very bright stars. And if you're observing really bright stars, you don't need a really big, wide aperture telescope. You just need a very small aperture that's very precise. But you also need a very wide field of view. Those huge telescopes out in Hawaii or Chile that can see, galaxies back to the dawn of time, the amount of sky that they can observe in a single shot is way smaller than your pinky fingernail held out at arm's length. This area of the sky that KELT telescope can observe is about this much in a single shot. It's 26 degrees across on the sky. It means our individual pixels are 23 arc seconds across. So what does that mean? Well, it means that this little blur down here in the lower right of this telescope of this image, that's the Andromeda galaxy. That's one of the biggest things in the sky that you can see, and it only occupies a tiny little bit of the field of view of our telescope. You can also see that all these other stars in the background there, they all kind of look like weird little sort of butterfly or spaceship shaped or triangle shaped images. That's because our field of view is so large that it is trying to focus a spherical area in the sky onto a flat CCD, and so it causes all these weird focal distortions of the stars. But what we have to do is go in there and measure the brightness of every single one of these stars, and we have to measure the brightness in every single image to a precision of better than 1% if we're going to hope to discover a transiting planet around those stars. We then, after observing millions of stars and making up lists of, say, hundreds of possible planet candidates, then what we have to do is go back with larger telescopes and try to verify that those stars really are experiencing these transiting events and confirm the existence of these planets. For that, we have a collaboration called the KELT Follow-Up Network. It is a collaboration of amateur astronomers and small schools all over the world. It involves places around here like Wellesley, Kutztown, Swarthmore. We've got amateur astronomers in Tennessee, a ton of amateur astronomers in Australia. They've been a lifeline for us. And what these telescopes do is these are typically 10 or 12 or 16-inch telescopes, and they take the information that we gather on planet candidates, and they'll go out and observe them with their telescope at a specific time and say, oh yes, this star really is experiencing some sort of transit-like dip in its light curve that tells us that there's a real possible planet around them. The amateur network is made up of people that some of them are involved in clubs just like this, and you don't need some incredibly expensive or incredibly sophisticated telescope. You do need to spend a little bit of money, but a lot of these are the kinds of things that easily a regular person can do, and you don't need to be in a perfect site to do it. You don't need to be on a mountain in South America. You can do it from suburban New Jersey. All you need is a telescope that you understand very, very well, and you understand how it operates, and you need just to wait for one of the few clear nights that happens. But we've got people like Mark Manner in Tennessee, T.G. Tannen in Australia, Yao Gregorio in Portugal. He's got a 12-inch telescope, and he discovered a Saturn-sized planet with us. So you can do this with small telescopes. You don't need to be in a perfect site. You just need to be in a place where there's good weather sometimes, once in a while, and you need to understand your telescope very well. So what we're doing is making these discoveries via the transit method, using this kind of measurement here. So what does that look like? Well, here's an example of one of our first discoveries. This is KELT-2AB. All the black points you see there are individual measurements that we took with the KELT telescope over the course of about 5 years. I think this is about a 5-year light curve. And we folded that light curve, we folded those observations on the period of those eclipses, of those transits. And the red points here are just the average of that data. So you see in the middle of this beautiful little dip in the brightness of the star, and that's the signature of a transiting planet. This one turns out to be a hot Jupiter. We're mostly sensitive to hot Jupiters. It has an orbital period of about 4 days. The planet's a little bit more massive and a little bit larger than Jupiter. It's KELT-2AB because this is one of those binary planets. It's not circumbinary, it's one of the first type, where there is a distant star about 600 AUs, 600 astronomical units, away from the host star, and you got the planet going around the host star and another star orbiting the two of them over a long, long time. So, and as a hot Jupiter, it's got a very high surface temperature, 1700 degrees in this case. We then go for these follow-up observations. These are the things that help confirm that what we saw in that first plot really is real. So these are observations by our follow-up collaborators. I think that's Swarthmore. I think this one is actually University of Wyoming. That one, I think, is actually one of our amateurs who just got this beautiful light curve. He has perfect observing conditions and got a gorgeous measurement of that planet going into transit. So we're absolutely indebted to these amateur partners, and it's become a really great way to collaborate between amateur and professional scientists to try to make these discoveries. So we have discovered 17 planets using this method. 10 of them have been published, 7 more are being written up right now. There's a lot of other good science that we do. We do things, by measuring millions of stars over long periods of time, we can discover pulsating stars and eclipsing binary stars and eclipsing disks and bright comets and a lot of really cool things. I'll tell you about one of those things now, which is that we have recently discovered the longest period ever eclipsing binary star. So for those of you who do backyard astronomy, you might have observed eclipsing binaries before. You'll see a star. Algol is one of the most famous. It's a pair of stars that are orbiting each other, and every so often one of them blocks the other. Well, most of them are known to be in orbital periods of a few days or weeks or months or years. This was a discovery that we made where what you see here is the observations from the KELT telescope over 1 year, 2 years, 3, 4, 5, and in the 5th year, the stars started getting dimmer, and in the 6th year, it just bottomed out. This is basically, it almost completely disappeared in our data. We then went back to other telescopes and found out that they had observed that same dimming over time. And this is happening back in 2012, 2014, 2015. So single eclipses have been seen before, where a single star seems to be eclipsing in some really weird way. But this is a super long eclipse. This eclipse is lasting 3 years long. Well, we were wondering, has this ever happened before? So we went into the archives. Harvard University has been assembling photographic plates of people who have made observations of the sky going back to the 1890s. And we went to that archive that has recently been digitized and looked at the records of this particular star to see if it had been dimming before. Well, this is an event that happened right around World War II. It is the green is a model, but you see over here that this star clearly dimmed by a couple magnitudes back then. There's actually a gap in data there because all the amateur astronomers who were taking data were called up for military service, so no one was looking at the stars during World War II. But we see a hint of what looks like an eclipse there, and when we combine it with our data, we find clear evidence where the data is overlapping, such that this is a 69-year-long eclipsing binary. 69.1 years. It is by far the largest, a record holder. But it's not just two stars orbiting each other, because if two stars were just orbiting each other every 69 years, the eclipse would take maybe a week, but it wouldn't take 3 years. So what's going on? Well, we got spectroscopic observations of the color of those stars, and we think what's going on here is that you've got a red giant star. That's the one that you're actually seeing. And then orbiting the red giant star is a companion star that's embedded in a huge disk of gas and dust. And as this big disk of gas and dust goes in front of the red giant star, it blocks it out, and it takes 3 years for this large disk to go across it. We think the disk is about 3 to 4 astronomical units in size, and the separation between these two is about 30 astronomical units. No, that's not right. No, I'd have to go back and double check the numbers. But it's very big, and it's a very unusual configuration. And these discoveries are very cool because they can tell us something about the size and shape and properties of these kinds of disks from which planets and stars form. All right, so to wrap up, let me explain why we're doing this. Because as we said earlier, there's thousands of planets known. What's the point in a few more planets discovered by the KELT telescope? This is why. This is a quote from a French philosopher, Comte, from back in the 1850s. And he was thinking at that time about the possibility of observing other planets around other stars and speculating about their conditions. And he said something interesting. He said, when he's talking about these planets, we see how we may determine their forms, their distances, their bulk, and their motions, all these planets, but we can never know anything of their chemical or mineralogical nature, and much less that of organized beings living on their surface, aliens. All physical, chemical, physiological, and social researches are out of the question in regard to the planets. At the time, he was right. With the technology of the 1850s, even if they had telescopes good enough to discover exoplanets, they couldn't say anything about their properties. What changed was the 1910s and 19-teens and 20s was the development of quantum mechanics. With the development of quantum mechanics, we learned how to measure the light that is reflected or emitted from a luminous object and break down that light into a spectrum and determine the composition and temperature and pressure and properties of those things. That's how we measure the temperatures of stars or the composition of stars. We can tell what they're made out of. So what we do with these KELT discoveries is something called transmission spectroscopy. When a planet goes in front of a star, 99% of the light from the star still makes it to the telescope. 1% of the light of the star is blocked by the planet. But maybe 1/10 or 1/100th of a percent of the light enters into the atmosphere of the planet, goes through that atmosphere, interacts with the molecules in that atmosphere, and comes out the other side and makes it to the telescope. And if we can disentangle the light that is filtered through the outer atmosphere of the planet and distinguish it from the light directly from the star, then we can pass that through a spectrograph and measure the chemical composition of that planet's atmosphere, and even say things about the temperature and pressure of that atmosphere. So this is a way for us to directly probe the conditions of these planets. Now, this is something right now that can really only be done with gas giant planets. Because you imagine this, you're looking for the light from the star that's passed through a tiny little annulus around the planet. And you need a huge amount of light, total light from the star, in order to break down and extract this tiny little signal. So the planets that KELT is discovering are the ideal planets for doing this kind of investigation because they're orbiting very bright stars and they're very big planets, and so they've got a lot of thick atmosphere that you can experiment with, that the light can pass through. What we're doing now is discovering these planets to enable us to refine these techniques, because in 20 years, we're going to be doing this, but not with gas giant planets, but with terrestrial-sized planets that might possibly have living things on their surfaces. And if we want to probe for the presence of living things, if we want to look for biomarkers, then we better be able to measure the composition of their atmospheres and look for elements or molecules in those atmospheres that would tell us that there's life there. Things like free oxygen in a reducing atmosphere, or as some people have discussed, looking for soot particulates that would be evidence of some sort of industrial civilization even. I'm not too hopeful about that, but there absolutely are ways to look for biomarkers in the atmospheres of these planets. And the techniques that we're developing now with the planets we discover from KELT are going to help us make those discoveries. So the next stage of this is the successor to NASA's Kepler satellite, which is the NASA TESS mission. TESS is the Transiting Exoplanet Survey Satellite. It's a satellite that looks a little bit like KELT. I like to think of it as KELT in space. It's going to launch in late 2017, and it's going to do exactly this kind of search for terrestrial planets transiting bright stars all across the sky. And it's going to be looking primarily for planets transiting small red dwarf stars that can then be gone, then you can go back later on with the much bigger telescopes like the upcoming James Webb Space Telescope and do those atmospheric studies to probe their atmospheres and try to understand what they're made out of and whether there's living things there. So ultimately what we're trying to do with this is look for evidence of life on other planets. We want to understand the properties of the planets themselves. That's an interesting question. But we really also want to try to understand whether life is unique to Earth or whether it's common in the universe. In order to do that, we have to be very careful about asking that question. Because as a lot of people point out, there could be life out there completely unlike anything on Earth, and we'd have no way of telling whether it's there or not. And that's absolutely true. So what we're trying to do in terms of looking for extraterrestrial life is to start off thinking about life as we have on Earth and trying to see if we can discover that. And only once we have a little bit of a handle on searching for life as we know it, are we going to start thinking about trying to look for other kinds of life. Life maybe based on silicon instead of carbon, or living in different kinds of environments. But for now, we're looking for life as we know it. So that means a planet that's orbiting a star. It means a planet that's got a solid surface. You need a solid substrate for chemical reactions to happen on. You need an atmosphere to provide enough pressure and thermal insulation for liquid water to exist. You need liquid water because that is by far, by orders of magnitude, the most versatile solvent for chemical reactions to happen in, and it's super common in the universe. You probably need a magnetic field because the magnetic field of the Earth is what protects us from a constant bombardment of high energy particles constantly hitting the Earth from the sun and from outer space. And if you don't have that, then everything here is going to get cancer within a few days. So you need something to protect you. Maybe you could have life living underground, but you're going to need some sort of protection. And then finally, you want to be in the habitable zone. You want to be at a distance from the star such that liquid water could exist at some point, because you need it to be liquid to provide the medium for the chemical reactions to happen that makes up life as we know it. So I'm going to skip through that and note that really what we've been doing with this is starting off with the ability to detect indirectly the presence of planets. And these are the small black shadows. These are using these indirect methods to infer the existence of planets that we can't really see yet ourselves. But ultimately what we want to do is we want to go back and directly observe these planets with a future telescope that it would be called the Terrestrial Planet Imager. It's something that is being conceptually designed now. If I'm very, very lucky, then at some point, maybe in 30, 40 years before I die, we'll actually be able to build and launch it. But that's what we would use to do these kinds of observations. Earlier, I showed you these observations of big hot gas giant planets orbiting far from the star. But what we want to do is to do this and look for Earth-like planets and directly measure the light reflected off the surface of an Earth-like planet that will tell us about things like whether there's continents or oceans or ice caps or clouds or maybe even living things. And for that, you need the pale blue dot. That's the idea of looking for a single pixel observation of a planet orbiting a nearby star. And we actually know what that looks like, because that's what this is right here. This is the last picture that was taken by the Voyager spacecraft as it was leaving the solar system and turned around one last time to point its camera at the Earth at the urging of Carl Sagan, who wanted to see what does the Earth look like from an unimaginably far distance. And so what you see here, this streak here is a beam of light from the sun that was scattered by the housing of the telescope on the Voyager spacecraft. But this is the Earth. That's the Earth, a single pixel observation. But that's enough to take that light and break it down with a spectrograph and measure the composition of our atmosphere and look for biomarkers that would tell us about living things. So that's ultimately what we want to do. So I hope this has been fun. There's the KELT-South telescope in a pretty picture, and I would be happy to take any questions. Yeah.
You said that, what we know today is that 70% of all regular stars have planets.
Yes.
Define regular stars.
Regular star. When I say regular star, I mean a main sequence star, so a star that's a regular part of its lifetime, that would be cool, then basically F-type through M-type. So that means stars that are a little bit hotter than our sun, down to stars that are quite a lot cooler than our sun. What that means is excluding giant stars, they evolved, when stars evolve off the main sequence. It doesn't count pulsars or white dwarfs or really hot OMB type stars. It's
includes multiple systems?
It includes multiple. It includes systems that are dynamically separated. That basically means stars that are either single stars or in multiple systems where their binary orbits are longer than about 100 years or so. Tighter than that that's a hazier thing. That gets into circumbinary planets, and we're still trying to figure those out. Yeah.
On average, how many planets does a star have?
That's a great question. So the question was, on average, how many planets does a star have? We have found multiple. So our own solar system has eight 8 or 9 planets, depending on who you listen to and what you're talking about. We have found multiple planet systems up to the size of 6 multiple planet systems. So we know they can be at least that many. It's really hard to come up with a solid number because those are just the planets that we've discovered, and there could very well be additional planets in those systems. We think that it's rare for there to be single planet systems. We have evidence that says that a single planet system, it just doesn't seem very likely. If there's a single planet orbiting a star that we've discovered, and we look at that star a lot more carefully, intensely over time, we end up discovering almost inevitably more planets. I would say that at least the median number of planets in the solar system is probably something like 3 or 4, but it could very well be 8 or 9 or even 10 or 15. We just don't know yet. That's something we're still waiting to find out. Yeah.
How long has it been possible in the history of the universe for terrestrial planets to have been formed? Maybe a better way to ask is how long after the Big Bang would you have enough heavy elements to form terrestrial planets?
Yeah, that's a great. A lot of people are looking at that. We think it should be relatively quick because some of the small galaxies that formed very early after the Big Bang, galaxies that formed within the first, say, 500 to 600 million years after the Big Bang, they actually would have a very quick succession of generation of heavy elements through early generations of stars. So as far as we can tell, there's no reason that a star as recently as, say, 1 billion years after the Big Bang couldn't have had enough heavy elements to form planets. Which actually prompts the question, well, if there's been, it's been 13.7 billion years, if, planets have been able to be around for, 12.5 billion years at least, then why are we only seeing ourselves now? Basically, why hasn't the galaxy just become chock full of alien civilizations and from planets that formed billions of years ago and had billions of years to evolve and adapt? We don't know the answer. It's something related to something called the Fermi paradox about if there's living things, then how come it just hasn't completely, exponentially grown and taken over the whole galaxy? And we don't know the answer to that. Presumably it means either life truly is so rare and so unusual that it really is unique to the Earth, or it means that there's something that prevents civilizations from expanding from one star system to another. I think, huh? Like the prime directive. Maybe they're just hiding. Maybe we just, maybe they've chosen not to reveal themselves. I actually think it's a lot more mundane. I think it's very likely that life is quite common based on what we've seen for the emergence of life on Earth. It happened very, very quickly. As soon as it almost could have possibly have formed, life seemed to have had to have evolved. Intelligence, however, the ability to think and construct things and be technologically capable of moving from planet to planet, that's something that we've only had for such a brief moment in time, really just the past few thousand years, that's something that does seem unusual. We've had life here for 4.5 billion years. We didn't even have multicelled organisms for the first couple billion years of that. So multicellular, sophisticated, evolved life that eventually becomes intelligent, that seems to be quick and unusual, and that I think is maybe more of the bottleneck, but that's speculation. Yeah.
I can just ask a follow-up.
Sure.
On that. Maybe there's just not enough incentive. Like when our sun about 5 billion years from now becomes a red giant, that would give us some incentive to do interstellar travel. So now we've been here about 4 billion years, so that's getting us to 5 billion years till intelligent life, and then another 5 billion years. So now we're getting close to 11 years.
I mean, absolutely don't discount just how hideously expensive it is to try to get off a planet. Right now it costs something like $10,000 to send a kilogram of anything into low Earth orbit. It costs roughly $1 million to send it to interplanetary distances in our solar system. And if you just extrapolate, it's about $1 billion to send a kilogram of anything into interstellar space. And that's based on the fact that it's just really hard to break against the gravity well that a planet exerts. And you better have a really good reason for doing that. I mean, you can send like a spaceship, out, which will cost a lot of money, but it's doable. But the idea of actually colonizing other planets, that requires a movement of material that's, arguably, is that worth it to a civilization to do that? Would you rather spend, half of our GDP sending people to Mars in a very precarious situation, or would you rather send robots that could do it for, a millionth of the cost, and you don't have a day of mourning when they die? So it's So space travel is very expensive and very dangerous and very risky. So I think that has something to do with it. And there's certain elements to fundamental physics that are going to ensure that that's probably always going to be the case, although that's, again, speculation. Yeah?
You said the wobble method helps you detect planets.
Yeah.
How can you tell how many planets?
Well, what's going to happen is if there's a single planet, you're going to have a nice sinusoidal pattern in the movement of the star towards or away from you. If there's two planets, you're going to have one sinusoid superimposed on another sinusoid. So you'll have basically something that looks like this over time, and then you'll have another and another. But signal processors, the people who work on things like radio and radar and communication systems, have been dealing with decomposing multiple signals for doing that for the past 70 years. So the science and technology of doing that's been around for a long time. The difficulty is making sure that all of those signals that you see superimposed on each other really are stable gravitational effects of planets and not other things like, say, star spots or star cycles on that star. That's something we always have to work very hard to make sure we're not being fooled by. Yep.
You said something about in 20 years you'll be looking for biomarkers in Earth-like planets.
That's the hope, yeah.
That's the hope. So what specific technological advances have to be made?
Two things. One is better spectrographs for measuring the wobble. Right now we can measure the wobble of a handful of planets that we're pretty sure are rocky, but we want to start being able to see even smaller signals caused by planets that are so small we absolutely know for 100% sure they are definitely rocky and they definitely have thin atmospheres. So we need to get maybe a factor of 2 to 5 better in the precision of our wobble measurement devices. That's one thing we have to do. The other thing we have to do is build bigger telescopes that can collect enough light over in a very stable way to basically do those spectroscopic measurements of the atmosphere. There's telescopes being built right now that can do that. One of them is the 30-meter telescope in Hawaii. There is the Giant Magellan telescope in Chile. There's the European Extremely Large Telescope also in Chile. And then there's the James Webb Space Telescope that will be launched into space in 2019, I think. And all of those in different ways will be able to do that. So those are the two pieces of technology. Spectroscopic observations of the atmosphere with a lot of collecting power, and also very incredibly precise and well-maintained spectrographs that can see very, very tiny wobbles. Yeah?
I worked on a big aluminum box for Princeton a couple months ago, and they told me it was a detector for doing that.
Yes, it was probably for Princeton, you said?
Princeton, he told me it was Princeton and I think Caltech, and they were going to put it on the tech.
Oh, okay, yeah.
Paying too much attention.
Yeah, so that's the thing. So these spectrographs have to be completely isolated. So these spectrographs are effectively taking light from usually a fiber that feeds from a telescope and passing that light through something that breaks it into its constituent, like a prism, and then you measure the patterns of that light spread across a lot of wavelengths. But if you have, if you're doing that in a spectrograph and the temperature in the spectrograph rises by, say, a few degrees, then individual pieces of metal in that device can expand and contract just based on thermal expansion of metals.
I think this was going to be in a cryogenic.
Exactly. So what you want to do is you want to keep them very, very cold. You want to keep the temperature stable to factors of millikelvin, even microkelvin sometimes, extraordinarily stable temperature, pressure. You want it vibrationally isolated so that the device that's doing these measurements can do so in a completely isolated and undisturbed manner. So that I would assume that that's part of that cryogenic isolation.
I thought it was like a big digital camera.
You usually don't need to isolate. So the cameras do need to be kept cool, but usually you can do that with just some very basic, like liquid nitrogen or something like that, without really needing to be building these extremely careful boxes. I would assume, but yeah. Yeah?
Considering that there's a speed to light and that in respect that we perceive it
Mhm.
with the telescope, if we can observe a star and possibly a planet in transit with that star, is it a possibility that having we perceive it now in hundreds of years ago, that planet and that star just disappeared?
So one of the big misconceptions that is really absolutely the fault of astronomers and physicists, and I apologize for this, is that, people say when you look out into the sky, all those stars, you're looking at light that's from millions and millions of years ago, and all those stars are dead by now. That's absolutely not true. The vast 99% of all the stars that you see in the sky are fairly close to us. They're within, say, 100 to 200 light years. So yeah, you're absolutely right. You're seeing light that's maybe a couple hundred years old, but it's not, millions of years or billions of years old. And a couple hundred years are it's very, very short in the astronomical sense. And so there's almost nothing that could happen to a solar system. If the planet is in a stable orbit around a star, it would take millions, or at least millions, really more billions of years for any normal kind of thing to happen that would disturb it, like for the star to evolve off the main sequence, for it to run out of its fuel, or some kind of planetary interaction to happen. Those kinds of things, either they happen within the first 1% of the star's lifetime, or they don't happen for 10 billion years. So the probability that we would see something just at the time, just right before something crazy were to happen to that system is just very unlikely. Maybe it could happen, but it'll be very low probability. Yes?
What is the nature of the Harvard data?
Yeah.
And how continuous is it? I was just wondering how serendipitous that a 61-year eclipse is going to be found and noticed in the data pre-massive storage of that kind of.
Right. So these are all of that data is in photographic plates. So these are glass plates that are maybe like this big, and these were the original plates that were used by astronomers back then. And these were taken at a lot of different places around the world. So they were not just a single telescope. It was a bunch of telescopes. I think the Harvard set is mostly in American telescopes. There's an Italian one with a lot of European telescopes. But people were taking, as soon as photography was invented, and people started putting, photographic cameras on the backs of telescopes, people took lots of them. And the early telescopes had fairly, they were not very large in aperture, and the smaller the aperture, the wider the field of view you see. And so it's actually not surprising that a relatively bright star like the one that we found happened to have been observed a number of times over many, many years. People were, at that time, were spending a lot of time trying to understand like Cepheid variable stars or other pulsating stars for which it was useful to have observations over a long time. So it turns out that this was just a fantastic archive of data that we were able to make use of. Yeah.
Is there any potential that I don't know if the right word is confirmation or observation of gravitational waves will help in the search?
The question was about gravitational waves helping. I can't really think of a way it can help. Well, gravitational wave discovery is incredible, and it's awesome, and it's going to be an amazing new part of science. But that's really going to be useful for doing things like studying the presence of black holes, the supermassive black holes at the centers of galaxies, the evolution of these supermassive black holes over time, and the remnants of stars that have exploded, like the pulsars and white dwarfs and neutron stars. I can't think of a way in which it will be particularly useful for exoplanet science, but maybe someone out there is thinking along better than I. All right, well, thank you all very much. I'm very happy to have been here.